Okay, so let us recap of the idea behind the bearing capacity. I think I mentioned the other day with lower bound and upper bound, equilibrium versus mechanism. So, the equilibrium is just the equilibrium of forces, which we saw one case. The mechanism is basically a rotation or a displacement case, where the condition of ultimate strength is achieved after failure. So, if you look at the case that we are going to look at is the second case. First case we have already seen this, we just equated the horizontal pressures and active pressure versus the overburden pressure on the right hand side, and then trying to equate, and we derived a simple formula which is giving the relationship between undrained shear strength of the soil with respect to the load at which the soil will fail because of the equilibrium case. And we have a reduced case where if the foundation is at the surface level, just like our offshore mud mats, where we just place it on top, we have reduced the equation to quite a simple 4 times the undrained shear strength. Now, this 4 is an empirical coefficient, depending on the failure mode we apply, it may be different, it may be 5, it may be 6. Now, this is for a simple case where phi is equal to 0, that means is a purely clay type of soil. Now, let us go back to one more simplified case where the failure is not by means of equilibrium, it is going to be a mechanism, that means it is a rotational failure. So, you can see from this picture very easily that the pressure applied on the bottom of the foundation, excavated foundation to a depth of d, and it is trying to fail by means of a shear failure along the lines of circular shape, what I have just noted down there. So, the mechanism is about the point of rotation is this, and the resistance is going to come from the shear strength of the profile up there. So, if you equate the moment at that particular point, and you can find out a equation, that is what is trying to be doing here, and the overburden pressure is same, Q naught is the depth times the the density of the soil. In this case we will take gamma dash, because we will be having the submerged condition. So, you see here we just write the equilibrium equation for the moment, you will get the Q u is equal to 2 pi C u, which is basically the arc length multiplied by the undrained shear strength, which is going to create the resistance against rotation, plus your Q naught, which is nothing but the overburden pressure. So, the resistance is coming from the friction part as well as from the overburden part, which is just, imagine if this whole thing is at the surface, then you will not have the Q naught there, because there is no overburden, and the acting moment is basically the moment due to the pressure multiplied by half the distance, just taking UDL to the point of center from this point of rotation. That is what we have done here, the active part and the resisting part. Resisting part is the shear friction or the shear strength, and basically the overburden time, and this is the acting moment due to applied load, which is Q times B times half the, basically this is acting at this point, at the middle point, and negated by or opposed by the friction plus. So, it is a simple mechanism by which we are trying to equate the, again this type of soil is basically purely clay type of soil, phi is not there. Based on this we got a basically if you take Q naught is equal to 0, bring the foundation to the surface, you get 6.28 times Cu. Now, the previous one we saw 4 times Cu, this one we are seeing. So, this is that is the lower bound, this is the upper bound solution. So, we can see soil can fail either way, but what we do not know is which one to select, and basically that is one of the idea, that the solution is bound by this much, from 4 to 6 it can vary, and it can be anywhere depending on the nature of soil, even if it is pure clay. Now, what we are going to just see, the next one is a generic soil, where you will have shear strength as well as the angle of internal friction, which is a generalized soil, we call it C5 soil, which in many cases you will find in real nature. When you are designing foundation, you are not going to get a pure sand, because it is not under your control. So, if you see this picture, slightly complicated. Of course, this picture goes back to as early as 1950s, where Terasaki first initially assumed certain configurations like what I am deriving, but later it became quite complex, because this is not going to be a so nice straight line. You know, several researchers have come up with different profile and different bearing capacity coefficients, and that is the history. But the starting point is something like this, where integration can be done very easily. So, what he has assumed is basically a triangle just below the foundation part, which is going to become part of the foundation itself. That is the idea behind it. So, you see the triangle drawn in light green color down there, is just half of it I have drawn just for clarity. Actually, the other side also will be filled with a similar. So, this soil below the foundation with certain height, which you could calculate, and the width is same as the foundation, this soil becomes part of the foundation load itself. So, it is going to just go down together. So, that is the first assumption, and instead of failure at the interface, see, if you go back to the first one, we were looking at failure along the vertical line, the line just coming down from the excavated surface. So, that is the place where we are equating the left pressure is equal to right pressure. So, that is the equilibrium line we were looking at. Instead, what Terasaki was looking at is basically a inclined surface joining A and B, which is something slightly different from what was the assumption. It all depends on, imagine if all this is water, the vertical line assumption is correct. If it is a very soft clay, it is going to go down like this, but if it is a C5 soil with good amount of sand and clay, probably the assumption made by Terasaki is very correct, because it is going to take a inclined failure surface, and that is why this is actually a reasonable assumption. So, the failure line is assumed from A to B. Now, we need to find a equilibrium of vertical forces, which will make them stable. The vertical force equilibrium is applied force is this P. You can calculate the unit pressure P by width, because what we are looking at is an infinite or a very long footing. So, we are not looking at the 3-dimensional effect, it is just a 2-dimensional effect, and the load applied plus the weight of the soil itself, which is going to become part of the wedge, the green wedge, which you can find out the vertical component, both of them is vertical. What we need to find out is the resisting component coming from the soil surrounding the foundation. So, which we can find out from a horizontal earth pressure, which we have learned about lateral earth pressure, if you know, active and passive. So, we need to find out what is Pp, from which we can find out a component which is resisting this movement of the foundation plus the wedge, which is going to go down. In order to do that, several things needs to be taken care. For example, when the foundation load is applied this way, this is going to be the surface is going to be active pressure wedge, whereas with this pressure, this side, this soil is going to go passive, because it is going to be pushed away. And basically, from the previous cases, the passive angle of failure is 45 minus pi by 2, and active failure is 45 plus pi by 2. So, that is what I have just summarized the parameters what we have learned over the last few classes, so that you will just take it and substitute. So, from this picture, if you take a elemental soil, we could actually equate the vertical pressure, which is nothing but your overburden pressure, gamma times whatever the depth, and if you are able to find out the horizontal pressure, which is 1 sigma 1 of the element 2, based on the lateral earth pressure theory for passive pressure, basically we will use our previous equations that we had. You simply substitute, sigma 1 will be equal to sigma 3 into Kp plus 2 times u, because this is not a pure sandy or clay soil. So, you will have both components. So, you can substitute and arrive at this equation we have derived earlier on, and then integrate this for the full depth of from here to here, because that is what is happening here. This is at that place, what we are going to do is integrate that, and that is what we have done. Ultimately, you will get the total passive pressure from the triangular wedge on the right hand side, based on the equation for what we derive from sigma 3 to sigma 1, which we have just got the approximate equations there. Once we know the Pp, then it is a matter of geometric calculation to find out what is the vertical force. So, in this interface between A and B, we have got two components. One is the resistance coming from the earth pressure, the second one is coming from the pure friction along the surface, very similar to what you just now did. In here, we have got a frictional, the soil is trying to rotate this way, but the frictional resistance along this surface is trying to resist it. Exactly same way, if you go back to this picture, we have got a frictional interface between A and B, and it is trying to push the soil up because it is unable to break the shear strength of the soil. So, basically two components of resisting, two components of acting. Basically the P plus W is acting downwards, and friction plus the vertical component of the earth pressure is going to be acting opposing or resisting the failure. So, what we need is just computation of that components, and which we have already got P p from geometry which I have drawn at this interface. You could easily derive just the geometric arrangements. Finally, you will come with the equation relationship between P p and P p vertical, which is just I have summarized in this at the last term here. The relationship between P p v and P p is basically cos phi, and that is what I am just giving you. You can go through simple geometric calculations of shifting from one to other, and basically here the beta and phi is used because you see here this is beta and this is alpha, and you have to draw both the triangles, superimpose and 90-degree shift. So, that is the idea behind. So, basically this is the diagram that will derive relationship between P p and P p v. Once you have this relationship, then you can simply substitute. This is the applied pressure from the foundation load, which is just load divided by the B by 2. I have taken half because for symmetry purpose you can take this half, you can just leave it the other side, otherwise you have to multiply by 2. So, I am just taking applied load at failure state, it is Q becomes Q u. So, that is the idea, and W will be calculated by the height of the triangle, and width half, and gamma is the density. So, that is the acting, and the resisting is the friction. The length is calculated in that particular the inclined length from A to B has to be calculated, multiplied by the shear strength, and basically the passive resistance, the relationship coming from P p. And once you have this equation, you simplify this in terms of K p. You go back to your geometric identities, substitute, expand this sin 90 minus alpha and all that resubstitution, you will get something like this. So, the first term is combining C u with all this replacement, you will get certain things inside, which is basically substitution, you get K p, and the second term is Q naught, which is your overburden pressure effect, and the third term is the self height of the wedge itself. So, from here you have to do a lot of substitution to get replacement like this. So, what we have is, one is the pressure, applied pressure, weight, the friction between the right side and left side are the inclined failure surface, and the last one is the passive resistance coming from the overburden effect. Now, you see here Terasaki has simplified this equation in terms of C u multiplied by a term just noted by N c, which is basically a bearing capacity factor, and N q and N gamma. So, what he was doing is just removing these complex equations and noting down by such simple notations, so that you can later calculate each one of them. N c, N q and N gamma, they are called bearing capacity factors for different purposes. So, you could actually plot these equations in terms of a chart for different characteristics of soil, you can go and pick up, and that is what you will see from some of the graphs, something like this. So, what I have done is just plotted in Excel. So, given an angle of internal friction for any sandy type of material, you can see here it is taking this kind of variations. So, you can calculate and then substitute. So, the idea behind this original equation is basically the passive earth pressure coefficient is known, then you can straight away calculate every one of them, and for that, if it is a pure sandy soil, the C component will go away, then it becomes even simpler. So, that is the first equation derived by Terasaki as a basic form of bearing capacity of a spread footing in 2 dimension. That means, the third or the length is very long, that the effect is negligible. So, that is the idea behind this. So, what we have now got a slightly complex shape of the triangle or the wedge which is resisting, and this work was done by several people. It started with Meyerhoff, Brinshansen, and then several other researchers. They found based on testing it's the shape is slightly complex and have lot of mathematical expressions. Ultimately, instead of looking at these, you could actually get some of them proposed empirical coefficients of varying nature based on testing and then comparison. And if you look at several codes, you go to either Indian codes or British codes, you will find these equations are plotted against either SPT values. Sometimes you have relationship directly with SPT values, or with the angle of internal friction, which is your phi angle, or with the shear strength. So you can find many ways of finding these coefficients, which can be used with this bearing capacity equation basically. Now, in fact, final form of equation for NQ is given like this. If you go back and compare this NQ in here, he simplified this equation in terms of something like this, and NC something like this, and N gamma. So, it is all final form of equations, but if you look at the later part of the like 70s and 80s, even these equations got modified, slight difference, but the numbers are not very big difference. Still many times we continue to use the work done by Terasaki for simple spread footing foundations. So, for all practical purposes, we will use these equations to calculate if it is sandy type of soil or C5 type of soil, where NC is related is with NQ, and you can find out NC from there. That is the chart which I was just discussing about. You could use it without any problem. So, you have to be a little bit careful use of this chart. Here only angle of internal friction is given, but though you can even get the NC values. If you look at the NC is the red color, 2, 3, 4, 5, I think it is about 5.14. If you calculate using this equation, you will get 5.14. So, remember we derived two cases for a pure clay type of soil. We got 4 for lower bound, 6.28 for upper bound. So, this 5.14 is somewhere in between. So, that is the idea behind. Now, the general form of bearing capacity equation. So, we have been looking at vertical loading, pure vertical loading, which is under rectangular footing. Instead, we could generalize bearing capacity evaluation in terms of load direction slightly inclined, or maybe sometimes you get horizontal loads, and then you will have a non rectangular shapes. So, we have a effect of shape coming into picture, and depth, it could be at the surface, it could be going down, load inclination factors, which is just I was mentioning about, and basically these three will be very common in any type of foundation, except maybe more primarily gravity type of loading from buildings. You may have a very little wind effect, but for offshore structures, even if it is temporary, you will see that a lot of wave and current loads will be coming. So, you have to take into account. So, this you can easily understand the first one very simple. For example, you take a circular shape of foundation. When you apply loading to a circular shape of foundation, the foundation tries to settle down because of the applied pressure. So, the settle down means the soil around the circular footing is trying to squeeze out, is not it? Very simple idea, because you are pressing down, what will happen? The squeezing out effect is going to be uniform throughout the periphery of the circle. Instead of that, if you actually take a rectangular shape, for example, just like a rectangular shape, the squeezing out effect will be more on the width side rather than length side, because the length is more. It is very similar to our the slab design. I think if you have learned about RC slab design, two-way action versus one-way action. For circular, it is multiple directions, everywhere you have a similar effect. So, that means which is better? Which is better is circular is definitely going to be better, because the effect of overburden all around is going to be effective. So, circular shape is always better, but construction wise not preferred, because it is quite difficult. That is why most of the time the spread footings will be either rectangle or combined rectangle, something like this. So, shape factor is very simple. Depending on the type and the shape of the foundation, you will be able to get the factor, it is greater than 1 or not, basically circular shape to rectangular, rectangular to strip. Some very rare cases we have triangular foundation, but what normally we do is we convert the triangular foundation into an equivalent circular shape, because it is very hard to find out the shape factor and then find out the capacity. In offshore applications, we have many cases circular, non-circular shapes like triangular and rectangular. Circular, very few cases we have used. So, you will have definitely the effect of shape from the bearing capacity calculated based on a simple long rectangle, I would say, strip footing, to various shapes needs to be taken into account by means of these factors. Depth factors is very straightforward, because the more that you go, you get a better soil and you get more overburden pressure. Load inclination factors basically is very important, because the more horizontal load, the frictional effect will come into picture, and failure will be earlier than actual vertical load. So, that is one of the important thing that you need to remember. So, all these things can be found from textbooks. I will cover only what is relevant for the cases that we are looking at. Some summary of the three cases: rectangular shape from strip footing to a square shape to a circular shape. So, basically you can see here circular shape is just substitution of B and L equal to same. So, you will get 1.2 times, both are same, breadth for a circular shape is similar, and for square shape basically 1.2. All other factors not getting so much affected. Basically the last one is the effect of the shape itself. So, you can substitute from a rectangular shape to square, square to circle. So, you have to remember these formulas. What are the coefficients from this to this? Only shape factor is applied here. Of course, inclination factors we have to calculate and multiply for each component separately. I think that is the derivation, that is looking at various factors, shape factors, the depth factors. You can use these formulas for phi is equal to 0 type, like a clay type of soil. Now, when you have SPT values are given, directly calculation of bearing capacity, I have just referred to several textbooks. You could not find, actually this is one of the application where you will be very useful. Instead of converting from SPT values to say angle of internal friction or CU, basically in this particular reference they have given a I think I have forgotten to put the in fact it is given in Bowles book, but the work is done by somebody else. Basically empirical relationship is given, directly can be used. One of the advantage of this particular method is he has tried to relate the foundation capacity with respect to a given settlement. If you look at this equations what we have derived so far, if you look at the whole equation, it does not tell at this time of failure or at this type of equilibrium what could be the potential settlement of the soil. So, that means the bearing capacity is delinked from the settlement what is going to happen. So, that is why later using the same load you calculate the settlement of the foundation and try to see what can be achieved or what you can actually allow as a settlement, then you have to come and correct the bearing capacity accordingly. So, that means that you got to do some extra work, whereas in this particular case he has given a relationship which actually given for the 25 mm the settlement basically normalized with respect to 25 mm. Only thing is this is an empirical formula, sometimes you have to be little bit careful, not very straightforward, depending on the situation you have to correct it. So, basic idea is this is one formula where you will find use of N60. So, from SPT you calculate the N60 and then apply that. Typically we need to just remember some basically the bearing capacity, what could be the range. So, if you look at very soft material at the bottom is about 75 basically soft and silt clay less than 75 kilonewton per square meter. So, if you convert into ton 7.5 ton per square meter, which is reasonably good load, but if you go to very soft clay you will find even less than that, like 5, 10, 15. Such type of soil, even if you apply a slight pressure will be settling down. So, the bearing capacity magnitude why you need to remember is just to keep in mind that when you are doing computation you should not come up with some large numbers. So, if you go back all the way to a very large number like 600 kilonewton per square meter. So, what it means is nearly 60 ton per square meter for a dense gravel or dense sand. So, that means you can place 60 ton load within 1 square meter of. So, you can imagine to get the 60 ton load how many concrete blocks you have to stack up, several, probably more than 10-15. So, that is the idea behind. You can understand the capacities of good sand is so much compared to soft clay. So, in between you will have several cases where you can keep the numbers as a reference values, but not exactly you are not supposed to use these numbers, because even after defining medium dense sand you will have a very large the range of values. So, you have to be a little bit careful, but just for information I have taken from the BS codes. It is quite reasonable. When you calculate you will get somewhere around here. These are the bearing capacity factors given by API, slightly different from what Terasaki has given. This is based on works by I think Meyerhoff, and when we are designing mud mats for offshore foundations, so we should use this. That is why I have reproduced that from the, for easy and convenience they also have given numbers, so that you do not need to read for given soil friction angle, you can straight away read it, but if you are not comfortable you can use these numbers. These are given for every 5 degrees, then you can just interpolate in between them. So, for examination point I will give you this table, so that you can just interpolate wherever you require. So, this the second thing is, instead of applying basically the inclination factor, API recommends you use the method of effective bearing area. For example, if you have only a vertical load, what will happen? The whole contact surface between the foundation and the soil will be positive compression pressure, isn't it, pure vertical load. But if the vertical load is shifted by say a few meters to one side, what will happen? There will be a non uniform pressure on one side is higher, one side is lower. So, what will happen whenever the pressure on one side becomes negative, that means the eccentricity is on too much. So, what will happen is the foundation is trying to tilt, but since there is no basically tensile stress can be taken by soil, what will happen? The foundation will start lifting off, and that area will not have a contact surface. Now, what will happen when this is trying to happen, when the foundation load is very far and foundation is trying to readjust itself? It's basically the contact pressure will start increasing in the area where the contact pressure is, contact surface is there. So, that means this load is same, only the location of load is shifting, and it is a continuous equilibrium. It will achieve its equilibrium as long as it is able to take it. If it is not able to take it, what will happen? The whole structure is going to overturn, and that is not very easy to find. Even today we have no solution for this. So, that is why API recommends an approximate method, simple approximation. You could use it, because to find out that the contact surface after achieving equilibrium is very difficult, because the soil settlement also happens simultaneous with the rotational behavior of the foundation. So, as the soil settles, as the foundation goes down, the soil gets better, bearing capacity is increasing, which we cannot model it unless you carry out a finite element analysis or a complex or carry out an experiment. You are not able to find out what settlement or what contact surface area, because it is an iterative process. So, at equilibrium there will be a reduced surface area and there will be some settlement, and basically the foundation will be stable if it is able to achieve the required overturning moment from the resisting pressure. Otherwise, the foundation will, or the whole system will just rotate and fail by overturning. So, this you see from this picture, there is a length and width of the foundation, and load is applied, of course load is applied eccentrically or load is applied with some moment, which both the cases are same. So, you can see here in this case the eccentricity is that applied moment divided by the normal load, or the other way around. If you have just load applied at eccentrically at the point here, then the moment is basically the load times the distance, which will give you the moment. So, because of that, the contact surface is only shown in that the hatch color area, and that is the area effective. So, after this what you will do is the vertical load divided by the effective area, that means the increased bearing pressure. But what difference we are making? For example, this you are going to do total load divided by that reduced area, but uniform pressure. But if you actually draw a pressure diagram, basically if you just look at a base of the foundation, originally so that is the area where negative pressure, because this is your foundation and probably that is your Q applied with moment, something like this, increased pressure, negative pressure. But now this may be say F2 max, this is F1 max, this is negative. Now, reduced area, probably you will be taking something like this, or you adjust it, that is the width finally available. What we are trying to do is or I can draw it something like this. Now, what we are ignoring is this slightly increased pressure, because we are going to take a, this is the average, not the peak pressure, because we are going to find out this by Q divided by A dash. A dash is nothing but the effective area after redistribution, which may actually not 100% correct, but that is going to be a quite small difference. So, we are just going to use that method. Otherwise, finding out the actual redistributed pressure is going to be quite troublesome. The reason why we need to do this in comparison to building design we do not encounter this problem, because the horizontal loads are very small compared to the vertical loads. The vertical loads are predominant, the magnitude is so huge that even horizontal loads are there, its negligible effect will be on the foundation. Whereas, in offshore structures, especially in the temporary phase, when the jacket is placed, is very light structure and the horizontal loads are predominant, because the reason why we make it light, because we make it buoyant. Remember, all the jacket members are made buoyant, so that when you place the jacket on water, it should float, number 1, and we make it vertical by just flooding little bit of water and we place it. So, at that time the jacket is not going to be very heavy, it is going to be very light structure. Now, vertical load is small, horizontal load is going to be substantially larger, and that is where we encounter this problem. Compared to onshore structures, we have a serious problem to resolve. That is why we have to learn a little bit more about the idea of eccentrically loaded foundation, but we cannot apply the conventional method of foundation design. That is why API has given this method, and it has suggested that this error in taking average pressure is not going to be that too much. But some of the times the method proposed by API also has been challenged, because the difference between the average pressure and the peak pressure what we have here is more than 10 to 15%. There are several other methods proposed by different codes, which we may discuss in the later part of the tutorial time. Basically, this is a chart given by API for one side or two side eccentricities. So, you could read the factors varying from 0 to 1 depending on the eccentricity factor. So, basically eccentricity is E2 or E1, E1 is, so for circular one is basically in this, because in any direction eccentricity is going to be same. So, that you read that, or if it is a single side E1 you read this, or a double one you read this, and basically the reduction in area is given as A dash by A is your original area, A dash is the reduced area, and basic idea is if E2 is 0, you will see that full area you will be getting. So, either you go by this line or go by this line depending on whether E1 and E2 are present. So, you can read the chart and get the reduced area. If it is a square one, it is very easy. If it is a rectangular one, you have to proportionate to the length and the width of the foundation. according to the multiplication factor what you are going to get. So, this chart is quite useful in terms of trying to find out a simplified solution, slightly approximative, but still practically very easy to do the problem. Basic idea is we will apply this method. The next one is slightly a different problem and also done by this researcher basically Davies and Booker several years back, I think 1976. This is predominantly a interesting problem in offshore. As I mentioned in the first few classes, these marine deposits for most of the the oil and gas deposited areas, the younger clay keeps depositing sediment particles and it just keep growing over the last 100 years or 200 years. You will see that as the new layers get deposited, the previous layer gets compressed, consolidated, and the strength increased. So, when we do the borehole, we normally find that first 30 to 40 meters of clay, you see a very low shear strength at the top, and then the shear strength keeps increasing in a linear fashion. Some places we have seen almost like 30 to 40 meter, from 5 kPa it goes to 40 kPa, something like this. Now, how do we use the knowledge that we have developed on bearing capacity equations? Because what we have derived three types of equation is just a uniform soil, either a clay type of soil with a constant shear strength to infinite or a very large depth, or a C5 soil with the characteristic same. Whereas here we have a soil where strength is low at the top and strength is keep on increasing, but then we could do one thing, we can take an average characteristics and do it, but whether it is true or not is not very clear. So, he has done experiments on this type of soil and come up with the empirical coefficient basically slightly improved. Imagine if you take the lowest shear strength, for example the top soil, and just finish your foundation design, you will get a bearing capacity of some amount, which is going to be very conservative, because you are only considering the low strength. Actually the strength increasing means is going to boost the capacity by some amount, and that is what is going to be taken advantage of that. So, he has proposed this method, we call it Davies and Booker method, is nothing but we go back to the original bearing capacity equation multiplied by the effect due to increasing shear strength by means of a so called strength factor because of the variation, and also he added a component called the rate of increase of shear strength. So, if you draw a picture, it will be something like this, basic profile, that is your seabed. So, this is the shear strength at the top and the shear strength at the bottom. So, this is the slope is the rate of increase, and that is what the total height is h, something like this. So, that is the formula that you can use that. So, C times Nc is the same basic form of equation for a clay type of soil, because the remainder will go away, and 1 plus Sc is the shape coefficient, which I think we have just derived for several shape cases. So, 1 plus Sc is calculated by the ratio of N gamma by Nc as per the Terazaghi equation, and B by L will come into picture. For circular foundation it will become 1, square foundation becomes 1, and N gamma by Nc will become 1.2 when you go and calculate. And basic idea is the calculation of Fr is given by a chart. I have tried to reproduce because it was a 1976 paper basically to be used for calculations. So, just took the values and replotted with respect to rate of increase, and the Fr value can be taken from this chart. So, for calculation purpose, there is an equation given by this particular paper. I think that can also be used in one of the references. The original paper was not giving, but the later researchers have come up with the equation for this particular graph, which I think for examination point of view I will try to give that equation, so that you do not have to read the charts from here. So, this method is very useful for many occasions where practical applications you will find this type of strength increase in several sites.